We now turn to the important topic of arc length. This is a topic that will come up again in Calc 3 and in subjects beyond, and it's usually dependent upon a set of parametric equations. So as we're going through, despite us considering a curve whose function is given by h of x, remember that x and y are still parametrically defined. So that means then that when I have my original formula for arc length, that it's going to require the bounds from x0 to x1. Let's assume that x0 is equal to x of t0, and that x1 is equal to x of t sub 1. And so as I am changing over my variables to the t variable, my x0 will turn into a t0, and my x1 will turn into a t1. And so this will become now the integral as follows. From t0 to t, the square root, and make yourself a big square root, 1 plus dy dt all over dx dt, the quantity squared. And this is going to then, we need a t on the outside, but we can't just put it there, so I'm going to do dx divided by dt. And you want to think of the dt's as canceling each other out. Of course, the dy dt over dx dt comes from our formula for dy dx in terms of t. And so this makes complete sense to put this in here. As a result, you'll now end up with the following: the integral from t0 to t1, the square root of dx dt all over dx squared, all over dx dt, the quantities squared. And of course, that's another way for us to write 1, plus dy dt, the quantities squared, all over dx dt, the quantities squared. Dx dt, and I'm now going to put the dt on the other side. This gives us the following: t0 to t1. I can pull out the 1 over dx dt times the square root of dx dt, the quantity squared, plus dy dt, the quantity squared, dx dt times dt. And amazingly, we can see that the dx dt's are going to cancel each other out. And so we will end up now with the integral from t0 to t1 of the square root of, let's write this as x prime of t, the quantity squared, plus y prime of t, the quantity squared, dt. And this is your formula for finding the arc length of a parametrically defined curve. Make sure, though, that you have a strategy for how to evaluate it. We know from our experience with integration by trigonometric substitution that the square roots are hard to manage. So there are a couple of things that we're going to have to do. We're first going to have to find x prime and y prime. Next, you're going to have to find x prime squared plus y prime squared. Then you're going to have to find some clever way of taking the square root. You are going to find that the hardest part about this is doing the square root because of the amount of algebra and manipulation to the expression that you are going to require. Let's take a look at an example to see how this is going to play out. A circle of radius 1 rolls around the circumference of a large circle of radius 4. If a point on the smaller circle is traced, the result is called an epicycloid. Determine the distance traveled by the point in one complete trip around the larger circle. The first thing to observe is that we are symmetric around the y-axis, and we are also symmetric around the x-axis, which means that I could go from 0 to pi over 2, And that would be a fourth of the total area that has been traversed. So I'm going to set my bounds to go between 0 and pi over 2 and multiply the final answer by 4. So my formula for arc length S is going to be as follows. It's going to be the square root of x prime of t, the quantity squared, plus y prime of t, the quantity squared dt. And I know that the first thing I'm going to need in order to evaluate this formula is x prime. I strongly encourage you, do not try to do this inside of the integral. You'll find it much easier to do the algebra outside. So if I find x prime, I will get -5 the sine of t plus 5 the cosine of 5t. So 5 the sine of 5t. Y prime of t is going to equal 5 the cosine of t minus 5 the cosine of 5t. And that's the first part, or the first phase of this done. The second phase is that we have to square x prime and y prime. And so x prime of t squared is equal to 25 the sine squared of t minus 50 the sine of t, the sine of 5t, plus 25 the sine squared of 5t. Y prime of t will give us 25 cosine squared of t minus 50 cosine of t cosine of 5t plus 25 the cosine squared of 5t. And then we know what we have to do with those two things is we have to add them, so that we end up with the following: 25 times sine squared of t plus cosine squared of t minus 50 times sine of t sine of 5t plus cosine of t cosine of 5t plus 25 sine squared of 5t plus cosine squared of 5t. This, of course, is going to equal 1. This right here is also going to equal 1. What's probably harder to figure out is what to do with the sine of t sine 5t plus cosine t cosine 5t. But if we recall our identity from pre-calculus, that the cosine of alpha minus beta is going to equal sine alpha sine beta plus cosine alpha cosine beta. So we're going to recast this now as the difference of the two, and I'm going to take 5t to be the alpha in this case. And so this is going to end up becoming the cosine of 5t minus t. The result is going to be 25 minus 50, the cosine of 4t, plus 25, which will equal 50 minus 50, the cosine of 4t. And now we have to do another little trick again, because we need to take the square root of this thing, and we cannot take the square root of the function that we have right here. So I'm going to use another identity, which I will write up at the top, and that is going to be the double angle formula for cosine of 2 theta, which is going to equal 1 minus 2, the sine squared of theta. I could have used 2 cosine squared of theta minus 1 if I wanted to also. That would have been fine in this particular setting as well, but this is more convenient for what we purpose to do, because we find that 2 sine squared of theta is going to equal 1 minus the cosine of 2 theta. And so this becomes a very convenient formula for us to use, since that's the way our function now appears to be. The form that it comes in is as 50 times 1 minus the cosine of 4t. And so in the place of where 2 theta is, I need to have this be 4t, which means in order to get it to be half of that, I'm going to need 2t in terms of the sine. And so this becomes 50 times 2 times the sine squared of half of the 4t, and so I get sine squared of 2t. This is now equal to 100, the sine squared of 2t. If you need to, this would be a good place to pause the video to make sure that you understand all of the calculations that took place. There were several that were of significance to us. After we squared our x squared and our y squared terms and added them, we used the Pythagorean identity in 2 locations. But then we also had to use the difference formula for cosine in this location right here. This produced something for us for which we can still not take the square root of. We need something squared, and the way that we do that is through the half angle or the double angle formula. And so using the double angle or the half angle formula, we found that 2 sine squared of 2t was going to be a suitable replacement for 1 minus the cosine of 4t. Let's take the square root now of this thing. And I will just deal with the principal square root. I'm not concerned with the plus or the minus. In any case, we're between 0 and pi over 2, in which case the sine of 2t is going to be positive. So that means now my arc length is going to be the integral from 0 to pi over 2 of 10 the sine of 2t. And remember that that only accounts for 1/4 of my area, so I'm going to need to multiply it by 4. The result is I get 40, the integral from 0 to pi over 2, times the sine of 2t dt. We can now take the integral of that. I'm going to leave it to you to work out those details, and we end up with negative the cosine of 2t all over 2, evaluated between 0 and pi over 2. This is going to give me 40 over 2 times the cosine of 0 minus the cosine of pi over 2 times 2. But this is going to equal 1. The 2's are going to cancel out, and this will equal minus 1. So I now end up with 40 all over 2 times 2, whereby I get that the arc length will be 40 units.